So we now go through unified chemistry. Again, this is the third practice paper in the series. So here we go. So first of all, they want us to give us the electronic configuration of the Fe2 plus ion. So quite straightforward, but do remember those two electrons which we've lost must come from the 4s subshell first. So dot and cross diagram for FeS2. So S2, you've got your sulfur going to have a covalent bond between those two sulfur atoms, which I've joined there. I'm going to just put a little S in there, like so. So you've got a single bond between your two sulfur atoms, but it's a 2 minus charge, so therefore I put two squares to show the electrons which are giving you the minus, so the two squares are there and there. So you need to show those differently. And then of course you've got the Fe2 plus ion as well. So combustion of coal contains traces of this compound, iron 2 disulfide. And it wants us to calculate the volume of SO2 gas produced in meters cubed if I combust 1 ton of coal. So first of all, we start off with a ton, but only 3% of that is actually FeS2. So that means I have got 30,000 grams of FeS2. Then I find my moles of FeS2, which is just mass over molar mass, to give me 250 moles. Now moles of SO2 produced is a 1 to 2 reaction, so I need to times that by 2 to give me 500 moles. And then finally I use my ideal gas equation to find my volume of SO2 that 500 moles will be at, and it tells me it's 100 kilopascals. We need to convert that into pascals, so it's 100,000 pascals. And we also need to convert my temperature of 50 degrees C into Kelvin, which is 323 Kelvin. Put all that in your calculator and you get 13.4 meters cubed. So here I have dimethyl sulfide now, and it's given me the displayed formula of a molecule of that. Predict the carbon-sulfur-carbon bond angle. So you may be thinking, what on earth can this be? But you should be able to relate this. So sulfur, of course, is in group 6, so we know that's related to oxygen. And the easiest molecule to relate this to would be a water. So the bond angle here we'll know is 104.5, and our explanation is pairs of electrons repel. Lone pairs repel more than bonded pairs, and on my sulfur I've got 2 lone pairs and 2 bonded pairs. Why is this compound, why does it have a low boiling point as in insoluble in water? Well, it's going to have a weak boiling point because the forces between the molecules are going to be London forces. There's certainly no hydrogen bonding, no permanent dipole because it's a symmetrical molecule, and therefore London force is very weak, so then you require a very small amount of energy to break and separate those molecules. And why doesn't it dissolve in water? Well, it can't bond to, can't hydrogen bond to water. If you remember, to be able to form hydrogen bonds, you need an OH, an NH, or an FH bond, which this molecule doesn't have. So now I need to find the amount of water in this hydrated salt. So it may look a bit scary, but it's actually quite straightforward. So they told you the percentage of water. So the rest of the percentage must be the ammonium iron 2 sulfate of 72.45%. So then you just find your ratio, really. So you put your percentage over the molar mass of the ammonium iron 2 sulfate here. Do the same for water. You get this ratio here, and that's in 1 to 6. So you've got 6 water molecules for every 1 ammonium iron 2 sulfate. Why would we add crushed limestone to an organic product? Of course, remember limestone neutralizes acidic soil. So actually that's probably a little bit of GCSE chemistry popping in there. Okay, so here we go. We now need to plan our procedure for testing for the ammonium ion, iron 2 and sulfate ion, and also carbonate in crushed limestone. So let's do carbonate first of all. To do that one, to the solid carbonate, we would add nitric acid and we would see it fizz. And that's the ionic equation here. Okay, for this one here, what we would do is we would take the sample, crush it up, dissolve it in water as much as possible, stir it up, and then filter off any solids. So we've got a nice clear solution coming through. And then we'd carry out the following tests on the filtrate. So first of all, sulfate ion, we would add barium nitrate. We would see a white precipitate of barium sulfate, and I put the equation here. For iron 2 plus, we would add sodium hydroxide solution. We would see a green gelatinous precipitate, and here's the ionic equation here. And finally, for ammonium, you would again add sodium hydroxide solution, but now warm it. You would produce a gas which, if you test with red litmus paper, it would go blue, and we have the equation here. Right, so we're adding aqueous sodium hydroxide to aqueous copper 2 sulfate. What would you see? You would see a blue precipitate, and that would be copper 2 hydroxide. It's believed that copper 2 ions in the mixture interact with protein molecules, preventing their growth of fungi. So how it tells me proteins are polyamides. How does it do this? Well, it would appear that the protein would form dative bonds or coordinate bonds with the copper 2 plus ion via either the nitrogen lone pairs or the oxygen lone pairs, and that would stop it growing. So first of all, why does the absorbance decrease? Well, if you have a look at the equation, iodine we know is brown colour in water. The concentration of iodine is going to decrease as the reaction progresses. Absorbance is proportional to the concentration of I2, so it wants me to calculate the concentration of I2 at the start and after 500 seconds. So to calculate at the start, I'm going to use this. So it tells me I start off with 1 centimetre cubed of 1 mole per decimetre cubed iodine. So that means I have 1 times 10 to the minus 3 moles of iodine, but the total volume of here is 100. So I have 1 times 10 to the 3 moles in 100 centimetres cubed. I times it by 1000 to get that into moles per decimetre cubed. So my initial concentration of iodine is 0.01. Okay, so now I know that it's going to be proportional. So I have this ratio here. So how do I find out this number here? Well, I know that 0.8 is proportional to 0.01. And I want to know what 0.18 is proportional to x. So in order to do that, we can say x is equal to 0.18 divided by 0.8 times by 0.01, and you will get 2.25 times 10 to the minus 3. So they want to plot the graph, shouldn't be too difficult. You'll get a straight line for that graph. Don't forget to label your axes, and I've given you a scale, approximate scale that you can use. So use your graph to find the order of reaction with respect to iodine. So you'll see it's a straight line, and therefore the order is 0 because the rate does not, because it's a straight line, it shows that the rate doesn't depend on the concentration of I2. Right, a 3-step mechanism has been proposed for this reaction. Complete the mechanism below. So they give me step 2. So in step 1, I have got to make this guy here, which I have shown there. And I know that in my slow step, well, actually I don't, but I know in order to get that, it looks like I'm going to start with this guy and H+. So you put those two together and you make this molecule here, which they've shown me there. So that produces this guy here. I know also I've got to use H plus here because I've generated H plus there as well. Okay, so I've got to get rid of this molecule here because it doesn't appear as a product. So that goes there. What haven't I used yet? Well, I haven't used my I2. So it's got to react with my I2, and I haven't made HI yet, so I've got to make that, and I've also got to make my product. There you go. That is the final step 3. So they now want me to show the hydrogen bonding between two H2SO4 molecules. So I've shown that there. Don't forget your lone pairs on the oxygens and also your delta plus, delta minuses as well. So then it says concentrated sulfuric acid is a powerful oxidizing agent and oxidizes hydrogen iodide to form iodine, hydrogen sulfide and another product. So the first thing we have to do is think about what other product could it be. You notice you've got oxygens in your sulfuric acid and no oxygens that you produce. So normally you would produce water, which I've shown there. Then you look at your oxidation states. The oxidation state of sulfur here is +6 and in hydrogen sulfide is -2. So that is a change of -8. However, iodine has only changed by +1. So therefore you must start with 8 iodine, hydrogen iodides to have an overall change of 8, of +8. So you start having 8 here, that means you're going to have 4 I2s. And then all you have to do is then balance your waters here and you need 4 waters. Okay, so you've now got to think about what compound A is going to be. So if you think about it, you going from here to here, you've got 2 of these molecules, quite straightforward, but you've lost an H there, which would have been there and there. So you've lost 2 H's there. The H's have appeared there. And you've also generated an oxygen there. So the oxygen must have come from this molecule here. So I've drawn that out and then I've added an O there. Another example where sulfuric acid is a catalyst, esterification is one. There are other ones as well. Right, okay, so we're now going to work out an enthalpy change of solution. So I put the difference in the mass readings for sulfuric acid, the amount of solution as well, and also your temperature. So you find your energy, which is the solution, mass of the solution, times 4.18 times 10.5, which is your temperature change. You then got your moles of sulfuric acid, and then you just do your energy change divided by your moles. Don't forget it's a minus figure, and I've converted this into kilojoules because when you look over the other side, they want the answer in kilojoules per mole. Okay, so we did this one on the previous page. So what's the maximum, has an error of 0.5 degrees, so what's the percentage uncertainty in the student temperature? So the temperature change they measured was 10.5, they measured temperature twice, so you've got to double your 0.5 times by 100 to give 9.5%. So I'm now going to use a greater mass of water. What will be the temperature change? So delta T will obviously be less because the same amount of energy, you've got the same number of moles of sulfuric acid being added, but that amount of energy is being spread over a greater volume of water. So delta T, first of all, will be less. However, your enthalpy of solution will be the same because you'll have the same energy per mole produced. And your change in temperature will now be 7.9 degrees C. And I've worked that out by taking the energy that I produce, but now this is being spread over 150 centimeters cubed. And if you rearrange that, you get delta T to be 7.9 degrees C. So when concentrated sulfuric acid is added to water, dissociation takes place in 2 stages. Explain the observation that 0.1 mole sulfuric acid has a pH of 0.96. Okay, so if it completely dissociated, our concentration of H plus ions would be 0.2 moles per decimeter cubed, because I would have produced 2 H pluses for every 1 H2SO4, and therefore my pH would be 0.7, which I have popped there. And therefore, which 0.7 is obviously lower than the 0.96 that it actually is. So it means that sulfuric acid has a higher pH than we would expect it to have if it was completely dissociated. And therefore, stage 1 you have complete dissociation, but stage 2 is partial dissociation. A student added excess sodium carbonate to sulfuric acid, what would they see and what would happen to the equilibrium stage 2? So first of all, you see fission, and what would happen to stage 2? Well, the H plus here would react with the carbonate ion, and therefore it would be removed, and therefore the equilibrium would shift to the right to replace the H plus removed. Okay, so now I've got to identify this acid C. So it tells me it's an aliphatic organic acid present in fruit juice. So the first thing I can work out is my molar mass of C, because I know the mass of it and I know the moles. So it has a molar mass of 192. But I also know it contains 7 oxygens. So 7 times 16 gives me 102. So I take the 102 away from 192 to give me 80. So we've got to figure out how many carbons and hydrogens I've got. So ballpark, I say 80 divided by 12, which is of course the relative atomic mass of carbon, gives me 6.6. So that would indicate I've got 6 carbons and 8 hydrogens, and I know I've got 7 oxygens. Right, it also tells me 1 mole of acid requires 3 moles of sodium hydroxide for neutralization. So that tells me I've got 3 acid groups. It tells me I've got a hydroxy group but produces no colour change, and therefore I must have a tertiary alcohol. And finally, my carbon 13 NMR has 4 peaks, so I've got 4 carbon environments. So this is the structure here. This one will work with your NMR as well, because you will have 1 here, carbon environment, then your other, these two are the same there, and then so you've got 1, 2, and then you've got these two will be the same, and then finally this one as well. So you've got 4 carbon environments, a tertiary alcohol, and the formula works. Right, so final page. What is the empirical formula of tartaric acid? Well, this would be an easy one to just count out and put the answer down. So you get C4H6O6, but remember it wants the empirical formula, so you've got to cancel that down to C2H3O3. Systematic name, well, if you have a look, your longest carbon chain is there, so it's butane-dioic acid, and you've got 2 hydroxy groups coming off here and here, so on the 2,3 carbon, so 2,3 dihydroxy butane dioic acid. Okay, then it wants me to react this guy with a 1,6-diaminohexane. So if you think you've got an NH2 group coming off here, C2H6, and then another NH2 like so. So this here is going to form a polyamide, and I've drawn that there. And finally, the polymerization takes place in 2 steps. First of all, they react together to form a salt. So what's likely to happen is that both of these hydrogens here, so this guy and this guy, are going to pop off to go on my 2 nitrogens like so, to give me the salt that I have put there.